Hello and welcome back to the channel. My name's Harry and I'm an engineer trying to land my first role in data science. In today's video we're going to be building an end-to-end machine learning model looking at doing classification and regression. I recently came across this dataset on car insurance claims. This represents car insurance customer data which we can use to predict if a person will make a claim and the cost of a claim if they do. This video is going to be broken down into 8 main steps. We'll start by doing some basic data cleaning and then we'll look at creating our train and test splits. Next, we'll do some simple exploratory data analysis. We'll then go on to more advanced data cleaning and pre-processing the data so that it's ready to use with our machine learning algorithms. Once that's done, we'll move on to the classification model selection. Based on the results of the model selection, we'll then look at doing some feature engineering. After that, we'll build a model pipeline so that we can automate all of the previous steps. Then we'll look at evaluating our classification model. And the final part of the video will be looking at the regression part of the project. Feel free to jump to the section of interest if you don't want to follow this project end to end. I'll make sure to leave timestamps in the description. So let's jump into a new notebook in VS Code. I'll first add all of the library imports that we'll need for the project. I won't go through these now as I'll explain these as we use them in the code. But if you do want to follow along, you can copy and paste the code from my code which I'll link below. You can see that I've downloaded the dataset as a CSV and I've put that in a folder called data. Let's go ahead and read that in using pandas and call it raw data. So that we can see all of the columns in the DF, I'll go ahead and set display max columns in pandas to none so that we can see all of the features. We can now take our first look at the data frame and see that there's 27 features in total. Some of these are probably quite obvious what they are, like age, income and home value, but some are a bit more ambiguous, like home kids, which is the number of children living at the policyholder's address, M status, which is the marital status of the policyholder, and TIF, which is the tenure of the policy. I won't go through them all now, as it will take too long, but I'll show on screen the definitions, so feel free to pause the video and read through them all. So we can now start with some basic data cleaning. We don't want to fundamentally change any of the data here, as we're still not split our data into our test and train sets, so we want to avoid any data leakage. I'll first create a new copy of the raw data, and then to make my life easier, I'm going to rename the columns to make them slightly more descriptive. I can do this by creating a dictionary with the existing column names as the keys and the values as my new column names. Then I can just use pandas rename method to apply these. So let's do .info on our DF to get a summary of the data. From this we can already see we have some missing values. We can also see that we've got a range of data types including objects, integers and floats. So as a first step, let's just check if there's any duplicate rows. We can see we've got one duplicate, so let's go ahead and drop that using drop duplicates. Currently, our currency-based values, like income, are formatted with the dollar symbol and commas. We want to remove these so that we can convert the values to integers. So I'll define the currency-based columns in a new list, then I'll create a new function that loops through each of these columns and uses replace and regex to find these characters and replace them with nothing. Adding as type after replace lets us then convert the value to an integer. I'll then go ahead and call the function, and we can now see that the dollar symbols and commas have been removed. Next, if we have a look at the data, you might notice that some of the values have a Z underscore prefix. We need to remove all of these so that they don't cause problems later. I'll first define a list, which includes all of the columns I've noticed these prefixes in. Then I'll create another new function. We'll pass the DF into the function as data and the columns as calls. We'll then loop through each of these columns in the DF, and again use replace and regex to replace the prefix with nothing. Finally, I'll then call the function, and we can see that we've removed the prefixes now. If we were working in the team in the workplace, we could work with our data engineers to make sure that we don't have these prefixes or currency formatting in the future. All this to say, we won't repeat these steps later when we build our data pipeline, as we'll assume that they'll be fixed in the future. The last step before creating the train and test splits is to remove any unuseful features. We won't be needing the ID feature, as this is just a unique identifier, and the date of birth feature essentially duplicates the age feature, so we'll go ahead and drop both of these. Now we can go ahead and quickly inspect our data frame after our basic cleaning. We can now proceed with creating our train and test splits. Since the author didn't provide a test set, we'll hold out a portion of the data to use as our test set. When creating our sets, we want to make sure that there's no bias in the negative or positive classes, so that the sets are actually representative of the customer data. To be clear, when I say the positive and negative classes, I'm referring to the target variable, which in this project for the classification is the isClaim feature. The positive class is that the customer has made a claim, and the negative class is that they haven't made a claim. Since we have a feature that describes the claim value of customers that have claimed, we can use this to do something called stratified sampling. This will avoid bias in the test set. I'll link an article in the description below if you're not familiar with stratified sampling, and I'll go into more detail about it and how to use it. We can create bins based on non-zero values for the claim value, as this implies indirectly that the isClaim feature is true. But we can double check this to make sure our assumption's correct. Let's create a mask to search for DF rows where the new claim value is greater than 0 and isClaim is equal to 0. We can see that this doesn't return any rows, which is what we'd expect. Let's now take a look at the distribution of new claim values. We can create a histogram using Seaborn by passing the new claim value, and we'll specify 10 bins to start with. We can see that this shows a heavy right skew, so when creating our strata bins, it might be wise to create non-linearly spaced bins to better capture the more extreme values with few instances. So for now, I'll use 10 bins by creating a list with the bin values, where the final bin will go up to infinity. I'll then just number these bins from 1 to 11 using np.arange. We can now apply these bins to the data using pd.cut, passing the new claim value feature, our bins, labels, and assign it to a new feature called claim value category. We can then see the distributions of our bins by creating a bar plot of our claim value category feature. It's important to have a sufficient number of each stratum in the dataset, or else the estimate of each stratum's importance might be biased. This distribution looks pretty good, so I'll go ahead with creating the train and test split now. We'll first create our X set, which is our predictors, by creating a copy of the data that we performed our basic cleaning on. We'll then create our Y set, which is our target variable, isClaim. Then we'll drop the target variable from our X set. We can then use scikit-learn's train test split, defining our X and Y, train test split, and then passing our X and Y sets. We'll use a test size of 20% or 0.2. We also need to pass the stratify argument for our stratified sampling, so we'll pass our claim value category feature for this. Great, we've now got our train and test splits. We can now just do a quick check to make sure that the positive and negative classes for the target distribution in the test set are representative of the train set. We can easily do this by summing the instances where true is equal to 1 and false is equal to 0, and then dividing by the total number of instances. We can see that the positive class ratios seem fairly representative of the test set, so I'm happy to proceed with this. Now that we've done our stratified sampling, we can go ahead and delete our bins feature from the data frame as we'll no longer need this. So we'll loop through the train and test sets to drop this. We'll now move into the exploratory data analysis part of the project. For the purpose of exploring our correlations between predictors and the target variable, we'll join xtrain and ytrain so that we have the predictors and the target variable in the same data frame. As some of the features are categorical, we won't be able to look at their correlation with isClaim. We can make some changes to the binary categorical columns to easily fix this. I'll create a list that defines the binary columns, then create a map that updates these values from text to zeros or ones. So in the mapping, you can see that I'm mapping yes values to 1, no's to 0, male to 1, and female to 0. And this is done with a dictionary. I can now apply the mapping to update these features by looping through each binary column and using pandas.map feature in a new function. I'll pass the data frame, the binary columns as a list, and the mapping dictionary. I'll then call this function and we can take a look at the updated data frames. So you can see for features like single parent, where we previously had yes or no values, we now have zeros or ones. So we can now go ahead and investigate how each of our features correlates with the isClaim feature. To do this, I'll create a heat map and limit it to show just the target variable column. We can create the correlation matrix using the pandas core method. This will create a correlation matrix for the data frame, and we can then sort the values by the correlation with isClaim. I'll then drop the isClaim row, as this will just show a perfect correlation with itself. I can then use the Seaborn heat map plot, passing just the isClaim column of the correlation matrix. I'll also pass arguments for the color style with CMap, set annotations to true, and set the color scale limits. We now have our correlations with our target variable presented as this heat map column. We can see the features with the strongest positive correlation are the ones that you might expect. We can't infer causation, but we can speculate. The total number of claims in the past 5 years might suggest that the more a person has claimed in the past, the more likely they might be to claim again in future. And then with license points, the more points they have might suggest a lower quality of driving and might reflect their likelihood to claim again in future. Then looking at the strongest negative correlations, we can see that home value is the strongest and income the next strongest. We can also see in the centre, with very negligible correlation, the red vehicle feature. I think there's something of an urban myth that relates to red cars and that they're more likely to be involved in accidents, but we can see from our data at least that that doesn't appear to be true. So now we can move on to some more advanced data cleaning and pre-processing the data so that it's ready for use with our machine learning algorithms. First, I want to drop any features that are unnecessary. It's a good idea to always remove features in your model if they don't help explain the target variable. In our case, we essentially saw that the red vehicle feature had no correlation with claims being made, so we'll drop that. Next, we need to deal with missing values. So let's start by seeing how many that we have. Summing is null shows that there's over 2,400 missing values, which is fairly significant for the size of the dataset. Let's see where we're missing values by looking at each feature. We can see from this that there's 5 main features that these are coming from: years job held for, income, value of home, occupation, and vehicle age. We know that 4 out of 5 of these are numerical features. As there's quite a few missing numerical features, using a simple imputer with a strategy like mean or median might be too naive for our model. We can try and be a bit more intelligent and use a k-nearest neighbours imputer, or KNN imputer. I'm sure most of you will be familiar with k-nearest neighbours, but if you're not, I'll add a link in the description that will go into more detail. Essentially, the k-nearest neighbours imputer will take what information it has available and interpolate this to impute a value. So to do this, we'll first create the imputer using 2 as the number of neighbours. We next need to define the numerical columns so that we can pass them to the imputer. We can do this by returning columns with data types that include number and then creating a list from this. Whilst we're here, we might as well go ahead and do the same thing for the categorical columns by selecting columns with object. We can now create the function to impute the values. We'll then pass the data frame, the numerical columns, and the imputer. We'll then fit and transform the data with the imputer and return the imputed data frame. We can now call this function, passing our xtrain raw data frame. It would be nice if we could check out the result of this imputation, so let's write some code to help us do that. I'll select the numerical columns from the raw df, and then filter by rows that contain null values in the numerical columns. We've now got a df which has missing numerical values which we can check the head of. We can now check the same rows, this time of the df that has imputed values. For example, we can see on row 11, where we previously had a home value of NA, we now have a value of 158,000. Good, so our imputer seems to have worked and the values are reasonable, so now we need to go ahead and deal with missing values in our categorical variables. For these, as there's less of them, I'm going to use a simple imputer and impute the most common value. We can do this by first creating a simple imputer and setting the strategy as most frequent. Like with the KNN imputation, I'll then create a new function, taking the data frame, the categorical columns, and the simple imputer. I'll then call the function and save the imputed categorical columns to a new df. If you did want to check the imputation, you could reuse the same code that we did for the KNN imputation. We can now join the imputed numerical and categorical data back together using pd.concat, and we'll save this to train imputed df. We can now check again for our missing values, and the result looks good as we can see that we've no longer got any. We now need to look at encoding our categorical features. Most machine learning algorithms need numerical data to work with, so we need to convert our text-based categorical data to numerical values. That's essentially all encoding is, but there's several methods to do that, and we'll have a look at some of those now. To help decide which encoding methods to use, let's look at how many unique values each categorical feature has. We can use our imputed categorical test df with nUnique for this. We can see that most of the features only have 2 unique values. This means that we can just consider these as binary values with a 0 or 1. Highest education has 5 different values, and an important thing to note here is that they do have an order or ranking. So getting a PhD, for instance, is a higher ranking than graduating high school. The presence of this ranking means that this is an ordinal feature, and this isn't true for all categorical features. For example, occupation has 8 unique values, but there's no ranking or order to them. The same is true for car type. For these non-binary, non-ordinal features, we need to use something called one-hot encoding. One-hot encoding creates a new column or feature for each unique value of an existing feature. Only one of these new features that's created is equal to 1, and hence why it's called one-hot encoding. So we can use one-hot encoding for occupation and car type, and we'll use ordinal encoding for highest education level. The remaining categorical features we use binary encoding. Scikit-learn doesn't actually have a binary encoder, but we can use the ordinal encoder as the first two values are 0 and 1, so it essentially achieves the same thing. So let's create three lists which define the columns for each encoder. First, the ordinal feature, then the binary features, and then the one-hot features. We can then create the encoders, but before we do that, we first have to specify the ranking that goes to the ordinal encoder. So this will be less than high school, then high school, bachelor's, master's, and finally PhD. For the ordinal encoder, we use ordinal encoder from scikit-learn and pass the rankings into the categories argument. We can then do the same for the binary encoder, this time with no arguments. Finally, we can use one-hot encoder and we'll set handle unknown to ignore and sparse output to false. We can now use the fit transform method of each encoder with the respective column lists that we defined earlier to perform the encoding transformations. I always like to return these outputs to a data frame so that I can check the output of the encoding. For this, you can just convert the NumPy array the encoder returns and assign column names from the lists that we created a minute ago. For the one-hot encoding columns, we need to use the getFeatureNamesOut method, as we'll now have several more columns than we did before. We can then concatenate these together and take a look at the results. The result looks correct, as we can see only numerical values now. We can take a look at the columns that one-hot encoding created. We can see the original feature name as the prefix, followed by the unique values. We can now bring our data cleaning together by concatenating our numerical data which we've imputed, and our categorical data which we imputed and then encoded. A really important step to check at this stage is if we've fallen into the dummy variable trap. This is really common when using one-hot encoding, and occurs because one of the new features that's been created is redundant and causes perfect multicollinearity. In simple terms, knowing all of the values for one of the one-hot encoded features allows you to perfectly predict the remaining one. A method to check for this is called the variance inflation feature, or VIF. We can create a new function to check the VIF of each feature that looks something like this. We can then call this function to see the results. We'll see some warnings, and this is a result of the dummy variable trap. We can see that all of our one-hot encoded features show a VIF of infinity, which is not what we want. This means that the feature has perfect multicollinearity. Generally speaking, a VIF of 5 or below is acceptable. There's a simple solution to this, and that's just to drop one of the features that the one-hot coding created. These features are often referred to as dummy variables or dummy features. Dropping one of these dummy features is often referred to as dropping the reference or baseline category. So let's go ahead and drop the first dummy of each encoded feature and then check the VIF values again. Good, we can now see that all of our features are well below 5, which is what we wanted to see. We can now go on to the more exciting step of model selection. At this stage, we want to try as many different models to see which is the most effective with our data in its current state. I'll create a list of classifiers with a tuple for each so I can include a name. You'll probably recognise most of these, as we've included models like logistic regression, random forest, and XGBoost. When we test these models, we want to use cross-validation. This is a good method for checking that the data has not been overfit. Cross-validation essentially splits the data into a number of groups that you define, and these are called folds. It then reserves one of these folds for testing and uses all of the others for training. By then averaging out the performance across each evaluation, you get a much better idea of the performance of the model versus just a single test. So that we can use the same folds for each test with each classifier, we'll create a kfold object with a scikit-learn kfold class. We'll use 10 folds and set shuffle as true. Next, we'll create an empty dictionary to store the results of each cross-validation test. We'll then loop through each classifier, run the cross-validation, and store the results in a dictionary. We can then convert this dictionary of our results to a data frame and take a look at them. A really nice visualization I like to use at this point is plotting these results on a box plot. This is really good for comparing the performance of the different models. We can do this by passing our results df to a seaborne box plot. We can also add some labels and a title to it as well. We can now clearly see our worst performing models were the decision tree and k nearest neighbours, with average scores of around 0.7 and 0.71. Our best performing models look to be the boosting models like XGBoost, gradient boost, and XGBoost, and this is quite common for classification problems like this. Although some of the other boosting models perform slightly better, I'm going to proceed with the XGBoost model for this video. I found that tuning the hyperparameters of XGBoost is much faster than other models, and this is better suited for the video. We'll start by looking at some feature engineering now. I've waited until now to do this because the feature engineering you want to use is often guided by the model that you want to use. For example, some models, like non-boosting models, benefit from feature scaling, but other models, like boost models and tree-based models, don't benefit from feature scaling as they're far less sensitive to it. Let's start by looking at the distributions of our numerical features. I'll write some code to plot histograms for each of our distributions with a facet grid using Seaborn. After doing so, we can take a look. I should mention at this stage that with most machine learning models, it's desirable to have a roughly symmetrical distribution. Immediately, we can notice that some of our features have a right skew to them, namely income, value of home, commute distance, vehicle value, policy tenure, and license points. If the features had really long tails, we might want to take the log of the feature. Here the tails aren't too long, so a common way to make distributions symmetrical is to take the square root of the feature. So let's try taking the square root of these features and see if we can improve the performance of the model. Let's first define a list of the skewed features, then create a new function to take a data frame, the list of the features, and loop through each feature in that list and compute its square root. We can then return the df with the updated features. I'll then plot these again using a facet grid so we can compare the distributions. We can now see the result of the transformations. The distributions generally look much more symmetrical. So let's use cross-validation again and see if the performance of the XGBoost model improves. We can see that the mean score is basically identical to the model that we didn't transform the data of. However, the scaling might benefit the regression models that we'll look at later, so since it had no negative effect, we'll make sure to build this into the model pipeline later. Next, we'll look at scaling the data, and we'll do this using scikit-learn's standard scaler. The process is nearly exactly the same as what we did with the square root transformation. If we then take a look at the scores, we can see that again the score is the same. But also like before, since it had no negative effect, and may benefit the regression models, we'll scale the data in the model pipeline when we build it later. Speaking of the model pipeline, we're now ready to build it. As you've seen so far, I like to do my data pre-processing in the notebook directly when building the initial model. Now that we've got a good idea of how we want to pre-process our data, we can do that by building a model pipeline. A last step I like to do is then to check our pre-processed data that we created directly against the output of the model pipeline. The first step is to define any custom transformers that we need to use in our pipeline. We saw that the square root transformation was ineffective, but we still want to use it as it might be beneficial to our regression model, and the same is true for our scaling. So the first custom transformer that we're going to look at is the removal of unimportant features that we did earlier. This will remove any features that we define from a fresh dataset for us automatically. We'll create a new class called column dropper. We'll inherit the base estimator and transformer mixing classes from scikit-learn in our definition. In the init definition, we'll take columns to drop as a list and assign this as a variable to the object. We can then create the fit, transform, and get feature names out methods. We don't actually need to fit the transformer, so we just return self with this method. With transform, however, we simply need to drop the columns that we don't want. We then need to do the same for our square root function, which is very similar to the process that we've just done for our column dropper, except this time we'll reuse the code that we did earlier to create the square root. We don't need to create a custom transformer for our scaling operation, as we can use standard scaler directly in the pipelines. So next, I'll define the pipeline for numerical features. I'll call this num pipeline, and in this is the data that we want to do our KNN imputation on. So in the tuple, I'll give it the name KNN imputer, and then define the imputer instance with n neighbours equal to 2. Next, I'll define the categorical features that need to be ordinally encoded. And as we'll remember, this was actually just the highest education feature. First, I'll just redefine the education ranking so that it's with the rest of our code, and then I'll create a new pipeline called cat-ord pipeline. First, we need to do our imputation, where you'll recall that we just imputed the most frequent feature. We can then define the ordinal encoding, making sure to provide the order with the categories argument. We can then repeat the step for the binary encoding, categorical features. And then next up, it's the one-hot encoding. So we'll first use the simple imputer, and then we can define a one-hot encoder. We can use the drop argument here to drop the first encoded feature, as we did manually earlier, to avoid the dummy variable trap. And we now have each of our pipelines. We now need to define which feature goes to which pipeline, and for that we can use scikit-learn's column transformer. I'll name this preprocessed pipeline, and then within a list in the column transformer, I'll define a tuple for each pipeline. First we can give the step a name, and then a transformer, and finally a list of feature names that the transformer should be applied to. And we're now ready to preprocess our data using our pipeline. We can do this using the fit transform method on our pipeline. At this point, if you're like me, you might want to check that the data from the pipeline matches the data frame that we created with manual preprocessing. We can do this by creating a df from the NumPy array that the pipeline generated. The only tricky bit is getting the feature names. As our one-hot encoder created new features, we need to use the getFeatureNamesOut method of the one-hot encoding. We access this by using the indexes on the preprocessing pipeline. We'll create a list with this and then join this to the list that we already defined for our numerical columns and for the other categorical columns. Finally, we can then assign these column names to our preprocessed df. We can now do the check to make sure that the dfs match by simply using the equals method on the manually created df and passing the xtrain-prepared df. When we run this, we can see that this returns true, which is great news as it means our pipeline is working and does the same as what we did manually. So it's now time to move on to hyperparameter tuning. We have our XGBoost model, but this is currently just using the default parameter values. Let's see if we can improve the performance of this model by tuning the hyperparameter values. To cover a large parameter space, we can first use the randomize search CV function, using random values from a defined range. If we can see an improvement in the model, we can then focus in on a smaller range of values using grid search. So first we need to define a parameter grid for the parameter values to try. Based on the default search values of XGBoost classifier, these are the values I'm going to try for my random search. I'll then initialize the classifier model and use error as the evaluation metric, as this is appropriate for binary classification. I'll use f1 as a scoring method for the random search, as this is good to use when the classes are imbalanced, as ours are. So I'll create a new scikit-learn scorer using f1 score. Now we can define the random search, so I'll pass the XGBoost model, the parameter grid, the scoring is our scorer, CV is 5, meaning we'll cross-validate each fit with 5 folds, and setting njobs as -1 we'll use parallel computation to speed up the fitting. We can now fit the random search model using xtrain prepared and ytrain, then print out the best parameters and the best score. This will take a couple of minutes to run, so I'll join you once it's finished. That's now finished running, and we can see the best parameters the random search found, and the best average cross-validation score. And this looks pretty good as a start, as we've improved the score based on the default model. We can now use grid search to focus in on final parameter values, now that we've got an idea of effective parameters to start with. So we'll repeat the steps that we did for random search, but this time, for the parameter grid, we'll define values around those that the random search found as the best model. Then we can define the grid search using grid search CV, passing the same values as before, except this time we won't need to provide the number of iterations, as grid search will check every possible combination of these parameters. So let's run that, and I'll join you once it's finished running. Now it's finished, we can see again that we've got some improvement, which is good. It is small, but an improvement nonetheless. At this point, we're now ready to make our predictions on the test set. We first need to pre-process the X test set with our pipeline, so we'll create X test prepared using fit transform on our pipeline and pass X test. We can then make a prediction using the best model from our grid search, which we can access from within the grid search object using best estimator. We use the predict method and pass our X test set. And now, for the moment of truth, we can check our final score. We can get the F1 score by passing our Y test and Y prediction sets. And there we have it, we've got our final score. This is pretty well aligned with the score that we got on our training set, which is good news. We can use a confusion matrix to better understand the predictions that our model is making. Let's go ahead and create a confusion matrix using Y test and Y predicted. then use confusion matrix display to create a plot. We can now see that our model made 1,375 true negative predictions and 270 true positives. The model's biggest weakness was false negatives, which it predicted 294 of. So from that we can see that there's still some room for improvement. We could look at going further with feature engineering or ensemble methods combining different models. But for now, I'm happy enough with this, so let's turn our attention to the regression model. Just a reminder, we're going to use the regression model to predict the value of a claim. We start this by filtering out our data to just include records that have made a claim. So let's create a new copy of the data frame we did the basic cleaning on. I'll call this isClaimData, and I want to filter it to just records where the claim amount is greater than 0. Now we'll just repeat the same steps that we did earlier to create the X and Y test and train sets. Again, for this we'll use a test size of 20%. Now we can pre-process our data using the pipeline that we created for the classification model. And next, we'll define a list of the most popular regressors. Like before, we'll create a k-fold object so we can use the same folds across the different regressors when doing cross-validation. We can then loop through each regressor, but this time for the scoring, we use the root mean squared error, or RMSE. This is a good performance measure for regression problems. We'll use it because it's also more sensitive to outliers than other metrics like the mean absolute error, or MAE. With RMSE, smaller is better. If we create a box plot for comparing regressors as we did with the classifiers, we can eventually see that linear regression and SGD regressor models were the best on average, as they both have the smallest RMSE of around 6,700. It makes sense that these two models perform similarly, as they're very similar in terms of the algorithms. As the SGD regressor has more hyperparameters that we can look at tuning, we'll proceed with using that. The steps for tuning the hyperparameters are exactly the same as with the classifier. We first create a parameter grid, then initialize the regressor. We can then create the random search with the regressor, the parameter grid, the number of iterations, but this time as it's a regression model, we'll use the neg mean squared error as the scoring. We'll then fit the model to the training data and return the best parameters and best score. So here's the parameter values we have, and we can see that the best score is around 7,600. So now, just like before, now that we've reduced the parameter space, let's use grid search to further refine our hyperparameters. I'll use a parameter grid based around the values returned by the random search, and then create the grid search. We can then fit the grid search to the training data and return the best parameters and score. We can see that this time we get a few warnings that the model didn't converge before the max iterations were reached, due to the combination of some parameters, but we did still get our best parameters and our score. Unfortunately this time, we've only managed to improve performance very slightly, but it is still an improvement nonetheless. Now we're ready to make our predictions on the test set. So let's first pass the X regression test set through our pre-processing pipeline, and then make our Y predictions using the grid search best estimator with the X set. We can then print the RMSE by measuring the mean squared error and taking the square root. We can also look at the mean absolute error, or the MAE, as well. And there we have it. Our RMSE was slightly higher than what we saw in the training set, but still fairly in line with it. As with the classification model, there's lots more opportunities to improve this. You could look at feature engineering, ensemble methods, investigating feature importances, and that's just to name a few. But to prevent this video being too long, we'll leave it there for today. So here we are at the end of our project. We've built two models, a classification model and a regression model, for predicting if a claim will be made and how much for, if so. And this is based on a variety of features and data about policyholders. I'll put a link below to my GitHub where you can check out this code in full. If you did enjoy this video or found it helpful, please remember to give it a like and make sure to subscribe for more data science videos in the future.